I'm moving on to cover the rest of the stuff on determinants. So at the end of class, whenever it was, Tuesday, we had, I had stated a formula for computing the determinant using cofactors. So I will remind you that if you start with an n by n matrix, then you can compute these numbers Cij, which are plus or minus determinants of one notch smaller matrices. So you start with your matrix A, and you cross out the ith row and the jth column, and you then have Aij is the matrix with these deleted. And so you can compute an n minus 1 by n minus 1 determinant here, however you would do that, and that defines the cofactor. And then the theorem is that if you fix an I, so you fix a row, then you can compute the determinant by taking the elements in that row and multiplying each one by its corresponding cofactor. So you sum on j, that means I'm summing across the entries of the ith row. And similarly, you can fix a j, and you can compute expanding along the jth column, same formula, but now I'm summing on I. So this is the formula. We used this thing. We used the ladder to define the determinant of a 3 by 3 matrix last fall. So the way we did a 3 by 3 is we've said, take the first column, take the first entry, and multiply it by this determinant. Well, that's what C11 is. If you cross out the first row in the first column, you're exactly doing the determinant of C11.
But we didn't have to do the first column. We could have done the second or third column and it would work, right?
That's what we're now saying, yes. But we didn't know that then. Right. And then plus, now we used to say minus this element times this determinant, where you had the first row and the third row. Well, that minus sign is built into the cofactor now. If you're in the 1, 2 slot, this is a minus. So, in principle now, if I gave you a 5 by 5 matrix and asked you for its determinant, you could apply this, and you would only have to compute, pick a row, pick a column, and then you'd have to do 5 4 by 4 determinants and multiply by the corresponding elements. And
4 3 by 3s.
now, computing 4 by 4s, not so much fun, but you could in principle do this. Now, why this is true, I'm going to come back to later today. So I'll discuss why these formulas are correct in a minute, but I want to actually use this stuff. So here's a neat application of the cofactor idea. So first of all, there's something that many of you learned in high school called Cramer's rule. How many of you actually have seen this?
Seen it, don't remember it.
Yeah, I don't remember.
Can you state
I've seen slides.
I saw it yesterday in the book.
Good ass. So Cramer's rule says, suppose A is a non-singular n by n matrix. And it gives you a formula for solving an equation ax equals b. Because a is non-singular, you know there's a unique solution for any b. Remember that? So, given any b, ax equals b has a unique solution. And if you happen for some reason to be interested in just the jth entry of that solution, so I could imagine some sort of application where you were interested in not the whole vector x, but just one component of it, there's a formula for it that looks like taking the determinant of some matrix Bj, which I'm about to tell you, and dividing by the determinant of A, which is non-zero. Why is the determinant not zero? Because the matrix is non-singular. And what Bj here is the matrix obtained by replacing the jth column of A with the vector B. So this is probably not efficient if you really wanted the whole vector x. You have other ways of solving this, like row operations. Augmented matrix do row operations. That's the most efficient way. But if all you wanted, if all you had was one particular value of x you cared about, this might be efficient if n isn't very big. Like if n is 2, or if n is 3. Right? So if I wanted to do, of course I haven't made this up carefully, but if my matrix A looked like this, suppose that were my matrix A, and I had the vector B, which is 1, 2, 3, and I wanted to know, well, of course, I'm assuming my matrix A is actually non-singular here. We'll find out in a minute if I screwed that up. And I ask you, what is x sub 3 if you're solving ax equals b? Well, by Cramer's rule, I would figure out what the determinant of A is. Presumably it's not 0 if I have a non-singular matrix. Has anyone checked what that is? Don't think it's 0. I'm getting 24 in fact for the determinant. So you guys can catch up in a minute. What do I do for the numerator of x? What am I supposed to do for the numerator?
Replace B in the third column of A.
Say again?
Replace the third column of A with B.
There you go. So where I had the third column, I put in the vector B instead. So notice if you were doing stuff by cofactors, it wouldn't be a bad idea to use the third column to do it with cofactors, because then you could use the same determinants and just multiply by different things to compute these two determinants. You see that? This is pretty cool. Is anybody checking me?
So if replacing B in that column makes it non-singular, then that entry is 0?
Makes
Or
it
is
singular.
Yeah.
Sure. Sure. Justin looks befuddled. Is there a problem?
No, I was just checking.
Oh, you checked?
Yeah,
Am I right?
you're right.
On both?
I only checked the top one.
Yeah, they're both right.
Hmm?
They're both right.
Okay.
Yeah.
All right, so this is, Cramer's rule actually comes up occasionally, and if those of you in applied science type things will see people use it. It's actually important for us because it's going to give us a way of figuring out a formula for the inverse of a non-singular matrix. But first of all, let me show you how you prove Cramer's rule. When I first was taught this material, they showed me a horrendous proof of what we're going to do next, A inverse. And then they derived this from that. And it was many years later that one of my colleagues here, who happened to be teaching business calculus, showed me the proof of this that was in the business calculus book. And it's the right proof. So
business got it right. The theory boys got it right.
Well, it was not Terry Boys, but it was people somewhere. There was mathematicians writing a math book for business students. So, Cramer's rule. I'm going to end up being sued now that this is on the public airwaves. All right, here's the idea. If I take the matrix A and write down its determinant, so I'm going to put the columns of A in where they belong, but in the jth column, I'm going to write the vector B. So this is determinant of Bj, right? So in the jth column, I'm going to put the vector B, and then I'm going to go on my merry way and put the rest of the columns of A. Okay. But what's B supposed to be equal to? It's supposed to be AX. And we know there is such an X because of the theory we did last semester. So I'm going to put in AX here. Now, how do we compute AX?
Well, that's just be linear combination of the column vectors.
So linear combination of the columns. So this is what we did at the very beginning of chapter 1 when we first defined matrix multiplication. Remember we said multiplying A by a vector takes linear combination of the columns. So if I put in this linear combination of the columns here, what happens?
You use the addition, you're adding multiples of columns, so it doesn't change the
Bless you. Well, you're ahead of me. So I've got A1, A2, and then in this jth column, I've got this ridiculous linear combination. I go on. What do we know about a determinant if you have a vector, one of the column vectors written as a sum?
Split up.
You can split it up by linearity. But when you split that,
Then A1 is going to be, in A1 will match one vector, A1, A2 will match it, the vector A2 is going to be 0, 0.
so anytime you have a multiple of one of the columns that's already there, you get 0.
Except in the J column.
So you're using the fact that if you repeat any if you have the same vector appearing in two places, you get 0. So as Reese is saying, the only term I'm going to get that contributes something non-zero is the jth one, because that's the only term that doesn't have one of the columns that's already sitting there. So I'm going to have exactly first column, second column, xj, aj in the jth column, and then up to an. And what have I got when I do this determinant? And what am I left with? End of proof.
How did you used to do it?
I already said that.
It's on tape.
Okay, so I'm now going to use this to derive a formula for A inverse. So using this, we get formula for A inverse. So you guys, when we first did stuff back in chapter 1, we had a shortcut for 2 by 2s. We knew how to find the inverse of a 2 by 2 matrix. And then we waited till chapter 4 to learn how to use a monster augmented matrix to find the inverse. But if you had arithmetic that was not particularly friendly, that could be actually rather a bear. Because if you start getting fractions that you can't avoid, it gets to be horrendous once you have matrices that are larger than 2 by 2. So it's actually of some use that generalizing the formula we had for 2 by 2s, you have the following formula. 1 over the determinant of A. Okay, A is non-singular, it's invertible, determinant isn't 0. And then what goes in the numerator is a matrix built out of the cofactors and transposed. So the ij entry of cof A is the ij cofactor there. So it's the cofactor matrix, and then you turn it on its side, you transpose it, and you divide by the determinant. So look, you don't have to do all these ridiculous monster augmented matrices. All you have to do is compute n squared cofactors.
Sounds like a computer problem.
This is not how computers do inverses. I already suggested you would get something worse than n factorial running time for an n by n matrix. It's very inefficient. But it's not so bad, and you do have a Weber problem to do this for one 3 by 3 matrix. And it's not so bad to do this for a 3 by 3. In fact, you might win the race if the arithmetic, if the determinant is something like 12. I bet you serious money that doing it by row operations, you're going to make arithmetic mistakes and have to do it 20 times to get the right answer. So this is actually not so bad. Notice that it does give what we did for 2 by 2s. What did we say for 2 by 2s? 1 over the determinant. And then what did we do? We swapped those and put negatives on those. Well, this is the cofactor of the 1, 1 slot. This is the cofactor of the 2, 2 slot. This ends up where it was with a minus sign. Why?
Because I plus j is 3.
So you're in the 1, 2 slots, you get a minus sign, but why is it a B instead of a C?
Is it transpose?
Because of the transpose. So the cofactor of this guy is minus C, but then you transpose, so instead of putting the minus C here, it goes down there. There it is. And so it works for n by n's.
So you wouldn't recommend doing that for like anything bigger than 3 by 3?
Not personally, no.
So why?
Unless there are lots of zeros, so that a lot of the cofactors are easy to do or something.
So what's the use of this?
Great question. The use of this is, it's a very powerful theoretical tool. Because what does this tell you? Well, it tells you, for example, that the entries of A inverse are what kind of functions of the entries of A. So we haven't perhaps seen this explicitly yet. I'm going to get to this later today. But the determinant is actually a polynomial in the entries of A.
What do you mean?
I mean that it's a polynomial in the entries of A. If you think of the entries of A as variables, this will be a polynomial degree n in the variables that are the entries of A. And each cofactor will be a polynomial of degree n minus 1. So, what's the quotient of polynomials?
The difference of their powers.
No. What's the word for a quotient of
Rational
polynomials?
function.
It's a rational function. So I will actually get to this in a minute. So the fact that I'm using here to be discussed shortly is that the determinant of A is a polynomial of degree n, assuming A is n by n, in the entries. So for example, for a 2 by 2, you get a polynomial of degree 2 built out of the entries of the matrix, and that works in general. So in particular, rational functions are smooth functions. They're infinitely differentiable, because polynomials are infinitely differentiable, and you have the quotient rule, you have quotient of infinitely differentiable functions are infinitely differentiable. So hence, A inverse is a smooth function of A. This will actually be important very soon when we get to stuff in chapter 6. Mm-hmm.
But isn't the degree on the bottom is bigger than the degree on
Right.
the top?
It
So
is.
doesn't that mean you'd like asymptotes?
Well, we're staying away from singular matrices.
Okay.
So, but you're right. If you looked at that polynomial expression and you approached a matrix that was singular, this would not make sense, right?
Right.
So how does it, is the given proposition supposed to fall out of Cramer's rule?
It is.
Okay, I think I'm missing it.
It's not immediate. So, do I take that as a request for y?
Yes, for me anyway.
Okay.
Were we supposed to not ask that?
I mean, it looks Cramer's rule-ish in as much as there's a determinant of A in the denominator. And so what we want to figure out is, how do we see entries of A inverse as entries of solutions of a certain linear equation? So, proof of the proposition, A inverse is defined by that equation. Agreed? So in particular, the ith column of A inverse is the solution of what equation? So A times A inverse equals identity. If I'm interested in the ith column, then I want that to match up to the ith column of the identity matrix. Agreed?
So it's the same as putting that in that other matrix.
No.
Like BJ.
AX equals EI. So if you solve that equation, the X is going to tell you the ith column of A inverse. Right? The ith column of the identity matrix is the ith standard basis vector. Remember, when you multiply matrix times column, you get that column of the product. Okay. Keep going. What's the jth entry? This is starting to sound like a Christmas song or something. The ith column is, the jth entry of the ith column is what?
It's, we use Cramer's rule.
So now we can use Cramer's rule. Is going to be the determinant of some matrix here over the determinant of A. So I'm going to call this temporarily A I J. So that's a script A. It's not our usual A. So what is script Aij going to be?
We're going to substitute, let's see, for J column, we're going to substitute E sub I, the I standard basis vector.
So this gets confusing, actually, right? So what am I supposed to do?
We're going to take A, the matrix A, and then substitute the I standard basis vector in to the J column. Right?
So what are we supposed to do? We're supposed to put, to get the jth entry, we're supposed to take the matrix that we get by putting this guy in the jth column of A. But what is the B? It's EI.
That's what I said.
I know.
We're just trying to confuse everyone.
So this is the matrix obtained by substituting EI in the EIO in the jth column of A. All right, so here you are, back at the ranch. You've got this matrix script Aij,
Relative scalar.
and it looks just like A, except in the jth column, I have all zeros except a 1 in the ith row. Everybody agree? How do you do the determinant of said matrix? How do you compute the determinant of a matrix that has a column that's almost all zeros? Yeah, but what method should I use to compute the determinant of this matrix? Cofactors. Using which row or which column? Obviously this column, because almost all the entries are zeros. So I'm only going to get one contribution if I do expansion in cofactors for this determinant using the jth column. So what do? I get one entry times its cofactor. So I cross out this row, I cross out this column of this matrix. Well, what's left when I do that? It's 1 times Cij, but the Cij is for this matrix, isn't it? But what's the rest of the columns of this matrix?
A.
So isn't this the same as that cofactor of the matrix A? Isn't this the same thing you would get if you took the original A, crossed out its jth column, crossed out its ith row, you'd have that cofactor of A. Well, the minuses are built into the cofactor. Yeah, thanks. So this is for A, the original A. Well, I think we're done. By Cramer's rule, the jth entry of the ith column of A inverse is so we take the determinant of this wacky matrix, divide by the determinant of A, and we just said that's exactly Cij over the determinant of A. So the jth entry of the ith column of A inverse is this matrix.
And we just need to flip the J and the I and the C. That's
So what does that mean? Well, that means that I should be able to take the cofactor matrix, divide it by the determinant, and get the entries of the inverse. But this is the jth entry of the ith column, so that's which entry of this matrix?
transfer.
It's Ji. Right? You're in the ith column, so the second index is an I, and you're in J down, so the first entry is a J. This is the Ji entry of this matrix. And it's in terms of the Ij entry of C, so that's exactly the same as your transpose to get the line up.
So that's an example of cofactors for you right here.
Again, though, even for a 3x3, so you have to do this for web work. I have no way to test that you're actually doing it, but you're only cheating yourselves if you just look it up on Wolfram Alpha or do it another way. I mean, part of the point I'm giving you the web work problem is practice actually doing these things for the case of a 3x3. So you're going to have to compute, but be efficient here, you're going to have to compute 9, for a 3x3, you're going to have to do 9 cofactors, but then once you've done them, you can use 3 of them to do this easily. So do the cofactors first and then do the determinant once you've got the cofactors, so that's not quite so bad. Okay, so as I said, in real life, you probably don't want to use that to compute the inverse, but it has theoretical tools, and it is sometimes actually a good way to do it. And in particular, if I know I have a matrix with a yucky determinant, I don't want to be doing it by row operations, because I know I'll screw up. You get horrible fractions in your matrices. So you actually have a few homework problems to turn in next week using this. That's also use of this material. All right. So before I go back to actually talk about where this formula for cofactors came from, I do want to make some comment here. So recursively, the cofactor formula tells us something nice about the determinant. So we've said that you can compute the determinant, for example, by, say, expanding in cofactors on the first row. So you would have, for example, A11, C11 plus A12, C12 equals up to A1n, C1n. Now, each of these things is itself a determinant of a smaller matrix. So you can imagine recursively working your way all the way down. If you keep doing this over and over and over again, you eventually get down to computing 2x2s or 1x1s. So what do you see happens? Well, if you start with a 1x1, if you just take the determinant of a 1x1 matrix, of course it's just the number. And if you do a 2x2, you get, of course, what we're used to. If you take the first row, for example, you get A times its cofactor plus B times its cofactor. And if you do 3x3, it's perhaps a little yuckier, but I'm going to do this for a reason. So I'm putting subscripts for reasons that you're going to appreciate in a minute. Or maybe you won't appreciate it. But. All right, so if you expand in cofactors, we did the column before, I'll do the row this time just to do something different. So what does it look like? Well, A11 times this determinant. And then A12 times the determinant you get with a minus sign, of course, when I cross off the middle column and the top row. So what do I have when I do that? With the minus sign, I'm going to have
A21, A33 minus A31, A2.
but we need minus that, right? So it's minus this plus this. So I'm going to have A23, A31 minus A2, whoa, A2, 1, A33. Plus, and then the last one, A13 times A21, A32 minus A22, A31. Now, all right, so you have 3 factorial terms here. 1, 2, 3, 4, 5, 6. But what do they all look like? Well, first of all, Jonathan, you see they start to look like 3 terms multiplied together, every one of them. So it's a polynomial degree 3 in these variables, if you like. But there's something more specific going on here. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Each one of them has a product of somebody from the first row, somebody from the second row, somebody from the third row.
Also true for the columns.
And also true for the columns. You're getting, each of the 6 terms has a product of 3 things, each of which is 1 from each row and 1 from each column. And what's going on then is you're taking all possible things of the form A1 somebody times A2 somebody times A3 somebody. And as Ken said, the 3 somebodies have to be 1, 2, 3 in some order. That's called a permutation of the numbers 1, 2, 3. And they're not all pairing with pluses. There's plus or minuses here. So what's actually happening here is that there is something I'm going to call sigma, which is called a permutation. So Haley's sitting here saying, oh my God, no. This is exactly what they're doing in Math 410 now. Sigma is a one-to-one map from the set 1, 2, 3 to 1, 2, 3. So you have to take 1 to somebody, 2 to somebody, 3 to somebody in a one-to-one onto fashion. That's what a permutation is. So here is the permutation where you're doing 1, 2, 3, stays in the same order. Here you fix 1, and you switch 2 and 3. And notice that got a minus sign. Here, what did I do? Here I took 1 to 2, 2 to 3, 3 to 1. So 1 went to 2, 2 went to 3, 3 went back to 1. And if that had a plus sign. Well, notice that's 2 switches. Cyclically permuting 1, 2, and 3 is doing 2 pairwise switches. You switch 1 and 2. So if you switch 1 and 2, you would have that. But now what do I want to do? I want to switch these guys. So now I'm going to have 1 going to 3, 2 still goes to 1, 3 goes to 2. And that's exactly what the permutation was. 1 goes to 3. Hey, I did the wrong one. I did it wrong. What was I trying to do? Sorry, I was trying to get 1 goes to 2. I got that. Now I want 2. I've got to switch these two. 1 goes to 2. Switch these. So then now 2 is going to 3, and 3 is going to 1. And that's what we wanted here. 1 goes to 2, 2 goes to 3, 3 goes to 1. So this was 2 switches. And so I get a plus sign. So in general, given any permutation, there's a thing called its sign, which counts how many pairwise switches did you make. And when we get to chapter 8, we're going to be doing this kind of stuff a lot, because everything's going to be built on determinants. So the sign of sigma here is equal to -1 to the number of pairwise switches. How about this one? Well, 3 stayed the same. I switched 1 and 2, so we got a minus sign. 3 stayed the same, switched 1 and 2, 1 pairwise switch. So you can see, recursively, this is going to keep on going if I go up to 4 by 4s. You can do a proof by induction. That, in general, a formula of this sort will hold when A is n by n. You still have a formula that says the determinant of A looks like a sum of plus or minus the product of somebody from each row and each column. And I'm summing here over all permutations of n numbers. Here I'm summing over all permutations of 3 numbers. There's 6 of those. That's my 6 terms.
And so, we do this for any, like for a 4 by 4, this will work?
That's what I'm saying. So I'm saying if you just use induction, basically, on what I've done here, if you assume that the formula holds for 3 by 3s, which we just got to, you can now do 4 by 4 by writing it in cofactors across the first row, and then using what we just did for all the 3 by 3s, you're going to see you're going to have somebody from the first row times such expressions involving only rows 2, 3, and 4. And so you're going to get exactly the same thing, where there's 1 from each row and 1 from each column.
So, also, maybe I'm misunderstanding, how do we determine how the 1, 2, and 3 switch?
I'm saying you get all possible switches,
Okay.
all n factorial terms,
Oh.
with a plus or minus according to this parity of what the switching is.
Why should we know that that parity gives when it's minus and when it's plus? Is that clear?
Well, it worked in this example.
Yeah.
It's because determinant is alternating. We said if you switch 2 vectors, you get a minus sign. And what this is doing is it's keeping track of how many switches of columns you've made to get it back in the standard order. So the fact is, every time you switch 2 columns, you pick a minus sign up in your determinant expression. And this is bookkeeping that. All right. Last gasp, and then on Monday we'll actually start the last section, which will not be on the exam.
This one.
Hmm?
What is?
Yeah, exam covers through determinants. So, a few comments on why the expansion cofactors works. And this actually, and you can read more about this in the book, but this is actually basically a proof of the theorem I stated when we started determinants, that there is a unique function with the 4 properties. This formula, basically, once we check it has the 4 properties, this formula tells you that there is a function. And it's unique because, in fact, as you know from doing row and column operations, you can uniquely compute a determinant if you put the matrix in triangular form. So if you had two different ways of computing determinants, and you followed the rules and took your matrix and put it in upper or lower triangular form, both those determinant formulas would have to give you the same answer, because they both behave by the properties that we used to compute it using the triangular form. So this actually, this formula actually proves existence and uniqueness follows as well. Alright, so here's what I want to claim in my last 3 minutes. So you take this formula, where you take the sum fix an I and take this formula. So this says take a matrix, take the entries in its ith row, multiply them by their corresponding cofactors and add. Check this formula satisfies properties 1, 2, 3, and 4. Now let's see, if you started with the identity matrix, would you get 1 for the determinant?
Yes.
You took the identity matrix, etc., and you'd expanded the cofactors on the first row, you would obviously get 1 times that cofactor, which is again 1 by induction. So the identity matrix works. If I multiplied a column by a scalar, if I picked one of the columns and I multiplied it by a scalar, would that scalar pull out of this formula?
Yeah.
When you got to that column, you'd have the constant there, and otherwise it would be showing up exactly once, again by induction in the cofactors. So property, that's property 2, that the scalars pull out. What if I switch 2 columns? That one is actually the hardest to check. So the column switch, you have to actually think a bit. And I'm not going to have time in my remaining minute to do it.
So we just check it out.
What about adding taking the jth column to be the sum of Vj prime and Vj double prime? Well, again, when you get to j here, you get a sum. And for all the other ones, that sum appears in the cofactor. So you get the sum there too. So these are obvious. This one, you actually have to do a little thinking, and it's written down in the book.
Why would it affect it at all?
Say what?
Why would it affect it at all? In that formula?
Because I'm certainly if I switch 2 columns, say the first and the second, then I have to keep track of the signs, comparing what the cofactors would be, were they for the first column or for the second. So when I'm away from those 2 numbers for j, I'm fine, but for the first and second, I have to think about it.
Callie, can you do the most basic, like in a 2x2?
Mm-hmm.
That you switch it in like.
Sure, we know that, but I'm
Right.
saying you have to check from this formula that it follows just from the formula. Okay, so more details are written in the book. And that will conclude our discussion of determinants. There is a little bit in the book I did not have time to do today, which is discussing how determinant gives a fudge factor for volume. So I need to come back and say that at some point.